Welcome back. We're going to move into Notebook C with this unit, and I'm going to open that up right now. I'm going to start sharing that. All right. So in this unit, we're going to take a closer look at RDKit, learn a little bit more about, or actually look at RDKit. In the previous unit, we looked at molecule representations, and we're going to look now at RDKit. And RDKit, once again, the questions are, what is RDKit? Second is what is an RDKit molecule or mole object? And what can I do with RDKit molecules? And our objective then is to find out how we can use RDKit to create molecules in Python. Now, RDKit is a library that was actually developed in C++ primarily, and has been around since the year 2000. And we'll be using a Python interface to RDKit. And RDKit provides what's called a molecule object. An object is a collection. Molecule objects contain information. They contain data, or objects contain information, data. They can contain methods, functions that they can do that are specifically designed that match well with those objects. In fact, that are designed to work with those objects. And typically the way we work with objects is we would have maybe start with object.data. So this would be something about the data that's actually contained in the object. Or we might have object.method and in parentheses arguments. So method is similar to a function, all right? So for example, we've already used lists. So my list equals, we've got the square bracket, and in that square bracket, we can put numbers, a list of numbers, but we have a method called append. So what we can do is we could append the number 1 to that list. Okay, so my list dot append 1, if we execute that cell, it's going to actually add the number 1 to that list. All right. So before we can get started with RDKit, we need to install it. So we'll need to hit the run button here. And notice we've got this exclamation point pip install RDKit. And if we're going to install a library and run it on Colab, there are some libraries that are native on Colab, but most are not. And this one is not. So to install it, we need to use this exclamation point to let us know that we're calling from outside of Colab. So I hit that run button. Once again, it's going to take 5 or 10 seconds to start taking action. And eventually we're going to start seeing some statements coming up here. And it tells me that it's downloading a program that the requirement's already satisfied for some things. NumPy and Pillow are two things that RDKit depends on. And then it says successfully installed. So we're good. And so we don't want all of RDKit. We just want one portion of it called chem. So chem is a set of functions in RDKit. And notice when we write about RDKit as a library, we call there's RD and K are all in capitals. But here when we use it, it's all lowercase. So I'm going to hit that run button. And now we've loaded that library, or we've imported the chem part of RDKit so we can work with it. Now, in the previous unit, we looked at smile strings and what they are. And what we're going to see is that if we give a smile string to RDKit, it can create an RDKit molecule object from that. And so in this case, we have the command methane. So that's going to be our variable. That's the RDKit molecule object we're generating. I'm going to say it equal to chem. So this is telling us we're pulling on the list of functions that are available in chem, and then mole from smiles. And notice the syntax is important here. The M is capitalized, the F is capitalized, the S is capitalized in mole from smiles. And we need to enter a value here for the string that will be methane. Well, remember in smile strings, we don't put in the hydrogen, so I'm just going to put in a capital C. And so we've created a mole object. Well, let's take a look at it. In this environment, we hit the play button, and it's CH4. That's what we expect for methane. Well, if we want ethane, think about that for a minute. Ethane is a 2-carbon alkane, so we just type in CC and then notice it says ethane here, so it's going to display it. Now, notice that it just displays a line. So this is the line drawing, and this is the default. for displays from RDKit. And a line drawing like this, the way I explained it in one of my classes, if it's a bend or an end, it's a carbon. And that carbon is going to have 4 bonds to it. So this carbon on this end is bonded to one other carbon, and the other 3 bonds are to hydrogens. The hydrogens are implied. All right. This end is also a carbon with 3 hydrogens bound to it, and the 4th bond to the first carbon. So here's a challenge to go through and create a series of SMILE strings based on what you learned in the previous unit. All right. So propane is a 3-carbon saturated alkane. So if it's just a straight chain, we just type CCC. Okay, I'm going to pause for a few seconds here. Think about ethene. So ene means it has a double bond. Do you remember what we used to represent a double bond in a SMILE string? Once again, it's going to be a capital C with an equal sign and another capital C. Cyclohexane, so that's a ring. So when we do a ring, we need to have a number so we can attach something to it. So we've got C1, so that's our first carbon on the ring. We've got 4 more carbons. And then we have another C1, and so that's going to form a 6-membered ring. Benzene, now benzene's aromatic. So in order to do that, we do lowercase. So we're going to do lowercase c1, and then 4 C's, and then another C1. This is going to give us a benzene ring. We'll see this in a minute. Acetic acid, well, acetic acid starts off with a CH3 group, so we have a capital C. Then there's the acid, the carboxyl group that's part of that. So we're going to put another C, and then in parentheses, we're going to put equals O. So that gives us the carbonyl oxygen, and then another O. And so that's going to be our acetic acid. And so let's see if we got it right. So this is, we're going to hit the run button here. Okay, we didn't get any errors, so that's a good sign. But what did we get? So the next cell, we look at propane. So there's the image of propane. Once again, it's a line drawing. So here's a CH3, CH2, CH3. For ethene, we hit the run button here. Once again, it's a line drawing. We've got just the 2 lines, and there's a CH2 on either end. These carbons have 2 bonds with each other, and then 2 hydrogens attached. Cyclohexane, so this is the ring where we have C1, CCCCC1, okay? So if I hit the run button there's our cyclohexane ring. And those of you who've taken organic chemistry know all about chair and boat conformations of that ring. And then benzene gives us a 6-membered ring with the 3 double bonds. So this is our aromatic ring. And finally, acetic acid. Hit the play button here. We've got our CH3 on the end here, then a carbon with a double bonded oxygen and an OH group. And so remember that in line drawing, the hydrogens bound to carbons are implied unless we tell it to do otherwise, and the hydrogens bound to oxygens or nitrogens are displayed. So now we're going to work with these RDKit molecules, and in this coding cell, we're just asking, we're bringing in some tools for visualizing, okay? So the IPython console, we're calling that IPC. It's very common in Python. There are certain abbreviations that are used a lot. IPC is used commonly for IPython console. We don't use an abbreviation for draw because it's not that many letters to write, all right? Then we're going to bring in here, and we're going to draw 3 different, or we're going to use 3 different functions from IPython console, and we're going to tell it to use SVG. I'm going to say that's true. We're going to add the atom indices. So that means from now on, whenever we have a line drawing, the numbers that go with a particular atom are going to appear. And then mole size, this just tells us the size of the molecules. We put a bigger number, we get a bigger structure. Now, one of the things that happens here is we have, if we were in Jupyter Labs, we'd be using the tab key a lot. In Colab, we actually get kind of an autofill function. So if I go next to acetic acid here, we want to use a method with the acetic acid. Now remember, we've already defined acetic acid. This is an RDKit molecule. So if I put a period next to that, then we have a whole bunch of options that come up here. We want to find an option that tells us the number of atoms in this molecule. So if I go down here and scroll down, I find a function called get num atoms. I'm just going to select that. And then notice we've got a statement here. Acetic acid has, and then an X, and then in quotes, heavy atoms. Now in RDKit, heavy atoms are anything larger than a proton, or anything larger than hydrogen 1. So if I hit the run button here, acetic acid has X heavy atoms. I did something wrong. I know my mistake. I need to have parentheses there. Okay, let's try this again. All right, acetic acid has 4 heavy atoms. So the mistake that I made there is that get num atoms is a function that needs to be followed by parentheses. Now, there are arguments we can put in that function and we in those parentheses, and we will do that, not right now. But even if you don't add any arguments, you have to put the parentheses for it to function properly. All right. Another thing that happens in Python is we can get help for what we're looking for. So what can we do with help files? Okay, we can put information inside a parenthesis next to help, and it's going to tell us a lot of information. So if I hit the run button here, then I get a lot of information about what we can find if we look at, wow, that is a lot. So this is help on a mole object. And so it tells us about the class mole, the molecule class, and other methods that it has. And then all kinds of tools and power. We're going to tap into a few of these. We'll be doing substructures later. So there's a lot of information in here. Get aromatic atoms. So these are some of the different functions we had. If we scroll down enough and I get lucky, we'll find the get num atoms function here. Yeah, get num atoms. That's one of the things we used. Okay, so these are all found if we click on the help. I'm going to move over here and scroll down to move past the help. All right. So the challenge in this next cell is to add an argument to your function to get the number of atoms that gives you the total number of atoms in acetic acid, including hydrogens. All right. And so first we want a variable where we assign the number of atoms, the number of heavy atoms. So we have X equals acetic acid dot get num atoms with a parentheses with nothing in it. So that's going to tell us that there are how many heavy atoms there are. If I want to know the total number of atoms, I go in this parentheses, and I'm going to say, in quotes, I'm going to say only explicit. Actually, I don't think I need quotes for this. Equals false. All right. And now I've got a print statement. It's going to say there are X heavy atoms, and that's the first variable we declared in acetic acid, and Y total atoms. Now notice in this F print statement, we've got words in quotes here, but anytime we want to have a variable included, we have to use curly cues or curly braces around that. So it tells us there are 4 heavy atoms in acetic acid and 8 total atoms. So if we want to know the total atoms, we say only explicit equals false, and it tells us how many hydrogens are there. Now, when we do the crash course on May 1st, this is where I'm going to stop. I'm actually taking bits of all of these notebooks and put them in the crash course. But for this video, I'm actually going to go through and go further with this. All right. So while I'm doing this, I wanted to mention that I do have the information here in front of me that you're looking at, but I have a second screen. And on my second screen, I have the finished version of these. All right. So I want you to notice here, I've got acetic acid atoms. So that's a new variable we're declaring. Okay. And I'm going to say acetic acid dot get atoms. So that's a method we can apply to our RDKit molecule object. I'm going to say print acetic acid atoms. So it's going to tell us something about acetic acid atoms. So when I do that, it tells us that this is a get atoms iterator object. All right. So an iterator is an object that contains values that can be looped through in the same way that, for example, a list is an iterator. All right. So let's find out how many atoms are actually in this list. So if I hit the run button here, I see that I've got 4 atoms. And since it's an iterator, then we can address the different elements in that list or items in that list by numbers. So the very first element in that list is 0. So maybe I should say the 0th element. Hit the run button, and it tells me that this, in fact, is an atom. All right. So what we want to do is we want to find out the methods associated with atoms. All right. So what I'm going to do here is I'm going to go in here and I'm going to say print atom. I'll put a period, and then I'm going to get some suggestions about what I can do with that. All right. And so let's say I want to know what the atom is. So I'm going to say get symbol. Okay, so this will be the symbol from the periodic table, and I have to give it parentheses. All right. And now I want to find its hybridization. Okay. So I'm going to say, if I scroll down here, I'm going to look for get hybridization. There it is. So I put it there, put parentheses after it. All right. And then I hit the run. And it tells me that the atom is a carbon and its hybridization is sp3. And so we get that by requesting this method get symbol and the method get hybridization. And those methods work on an atom object. Now we can also loop through all the atoms in acetic acid atoms because it's an iterator. I won't say it's exactly a list, but it is an iterator. All right. And so I'm going to say for atom in acetic acid atoms, print. Now this is an F print statement, atom, and then this is our variable, atom get symbol, has hybridization, and then our next variable, atom get hybridization, is going to go through all the heavy atoms in acetic acid. So notice it says here atom C has hybridization sp3, and it describes the hybridization on the other 3 atoms, and it got them right. So that's pretty great. Now, another thing we might want to do is find the bonds in acetic acid. And so we can create another iterator. Acetic acid bonds equals acetic acid dot get bonds. All right. And then I'm going to ask it for the first bond in acetic acid, the 0th bond. Hit the run button. And it got it. And we don't know anything about it because we didn't put a print statement in there. But if I say bond dot get bond type, and hit execute, it tells me that this is a single bond. So there's a challenge here to use a for loop to print information about each bond. And for each bond, you should print the starting atom symbol, the ending atom symbol, and the bond type. And your final output should look like this. Between bond C and C is a single bond. Between bond C and O is a double bond. Between bond between C and O is a single bond. All right. So I recommend that you pause the video at this point and give yourself a couple minutes to think about this. All right. So we've got this iterator, acetic acid bond. So that has a list of all the bonds that are found in acetic acid because we generated that with our statement up here. And so for the bonds, what we're doing is we're going through one bond at a time. We say start underscore atom equals bond, and then we have get begin atom. And so this is one of the functions we can call. And the end atom then is going to be bond get end atom. And so this knows which atom is at either end of that bond. Then the bond type asks us to get the bond type for that exact bond. And then we have a print statement, print, and then an F statement, the bond between the start atom dot get symbol. Okay, so that's going to bring up either a carbon or an oxygen, and the end atom, and it's going to bring up, again, either a carbon or an oxygen, because those are our 2 options from this iterator, is bond type, and it gives that bond. So we hit the run button. and we get the statement we're looking for. Now, it's possible to have a lot of fun with RDKit. And so we're gonna go back, or we're gonna go back to a molecule we declared before. Before we declared benzene, that's earlier, so it's just a 6-membered aromatic ring. What we're gonna do is we're going to create pyridine from benzene. All right, and so what we're gonna do first is we have a variable pyridine, and we're gonna assign it chem and then RW mole. That's a method that enables us to make a readable, writable molecule of whichever molecule we put in there. Well, we're putting in the RDKit benzene molecule object. All right. So if I do that and I print that and say pyridine, oh, it still looks like benzene. We haven't changed it yet. So what we need to do is, oh, the atom indexes aren't showing up. I think that's probably because I never actually executed this this cell here. So I'm going to execute that cell. Okay. Notice once I executed, there's a check mark next to it. So I come back down where I am. I'm going to execute this cell again. This time it shows up with the numbers. All right. So what I'm going to do is I'm going to modify this atom 0. Okay. So I'm going to say atom equals pyridine.getAtom with index 0. So we're just selecting that atom right there. And then atom dot set atomic num. So we're setting the atomic number to 7. So we're changing it from a carbon to a nitrogen. All right. And once we do that and hit the run button, there's our pyridine. All right. And we can actually, now we have that structure, and we can use from the chem part of RDKit, we can use the mole to smiles. We had mole from smiles before. We can use mole to smiles. Hit the run button here, and we can see that we've got, it's all lowercase. We've got a C1, C, C, N, C, C1. So that's our pyridine ring. So here's another challenge, which is to change another atom in the pyridine ring to create pyrimidine. All right. So pyrimidine actually would be a 6-membered aromatic ring with a nitrogen at position 2. And so what I'm going to do is I'm going to modify the pyridine molecule. So pyrimidine equals chem.rw mole, and I'm putting pyridine here. Go ahead and type that in. Notice that it gives me the option of putting that in. And then I'm going to select a particular atom on this pyrimidine object we've just declared. And the atom I want is the one at position 2. So I'm just going to put a 2 in that box. So go ahead and do that. And then I'm going to change the atomic number of that atom from a 6 to a 7. So I just put a 7 there. And then and so I've got pyrimidine is equal to chem.rw mole pyridine. So the pyrimidine is an RDKit mole object at this point that we can actually read and write on. And we're going to go through and we're going to change atom 2 on the original ring from a carbon to a nitrogen. And I hit the run, and there's our pyrimidine ring with 2 nitrogens in it. All right. So the last thing we're going to do in this notebook is we're going to combine 2 molecules to find a new one. Now, what we're going to first do is we're going to create a carboxyl group. And so in order to do this, I've got carboxyl. So that's our variable. We're going to make a new RDKit molecule object called carboxyl. We're going to say equals chem. So this is calling on the chem part of RDKit, and then mole from smiles. We've used that before. And then in parentheses, inside quotes, I have the expression for a carboxyl group. So this is a smiles expression. So there's a C. There's an equal O inside the parentheses. So that oxygen is double bonded to this oxygen. And then the final oxygen is single bonded to this oxygen is double bonded to this carbon. Sorry, I misspoke. And finally, this oxygen is single bonded to this carbon. So that's our carboxyl group. And when I run this, I can see we've got a carboxyl group here. Now notice This isn't a complete molecule because this carbon only has 3 bonds. There's room to make another bond, and that's important for our next step. So in our next step, we're going to combine 2 molecules. What we're going to do is we're going to create a new RDKit molecule called combined. Once again, we'll use the chem sub-library of RDKit and a method called combine moles, all right? And in order for this method to work, you have to have 2 RDKit molecule objects to combine. So I'm going to do that. So if I hit run, you can see I've got the benzene ring and the carboxyl group, and they're just kind of all there. Notice that all of the positions are numbered. So now I'm going to make this editable. So I'm going to say editable mole equals chem.rw mole. Remember, rw mole means read write mole. And we're going to use this mole object combined, and that becomes our new structure, editable mole. Now the way it looks doesn't change, but now we can do something about it. And we can take this object, editable mole, we can add a bond. So we're going to bond position 0 in the benzene ring with position 6 on the carboxyl group. And we're going to tell it that the bond order here is going to be a single bond. So we do that, and since we didn't tell it to show us the molecule, it tells us the number of heavy atoms. All right. And then if I hit the run button here, you can see we've got our benzene atom, but the dotted line means that it's not formally what we call calculized. Okay, keculized. And so we have a function called sanitize mole, or a method in the chem library called sanitize mole, that will clean that up. And when it does, we now get our benzoic acid. Now, the final challenge we're going to do here, protein phosphorylation happens when we attach a phosphate group to the OH group of either serine or threonine or tyrosine. So what we're going to do here is, for this challenge, we're going to modify the tyrosine module. Actually, I should have said molecule, to add a phosphate group to the OH group. So in order to do this, I need to go to PubChem, and I need to get the SMILE string for tyrosine. So I'm going to open up a new tab. I'm going to type in PubChem. I've been going there a lot. And so I'm just going to type in tyrosine here and search. And the output that comes back, one of the options is the SMILE string. So I'm just going to copy this. So that's our SMILE string for tyrosine. So once again, this is on pubchem.ncbi.nlm.nih.gov. So here's our SMILE string. Notice it's I guess it's the 3rd thing or 4th thing on the list here below the names. So we go back to that Colab notebook. So we have tyrosine equals chem.mole from SMILES. So we're going to create an RDKit mole object for tyrosine. So I just paste in that string. Notice it's between quotes. It has to be. And when I do that and hit the run button, then we see the tyrosine molecule. And notice it's not charged. So it's the NH2 is not charged. The OH here is not charged. And we've got the OH group, but this is tyrosine. The next thing we want to do is we want to create a phosphate group. So we need to create a phosphorus bound to 3 oxygens. Now, we need to keep one bond open, pardon me, in order to bond it here. So what I'm going to do, pause the video and see if you can think what we want to do here. All right, so we've got a P, and then attached to that P, I'm going to open a parentheses, put an equal sign with an oxygen, so that's a double bonded oxygen. And we're also going to have a single bonded oxygen bound. And then finally, we're going to have another single bonded oxygen. So this double bonded oxygen is bound to the phosphate. The single bonded oxygen is bound to the phosphate. Those are both branches. And then the final oxygen is also bound to the phosphate. And so when I hit the run button, I get our phosphate, and it has 3 oxygens bound to it plus a hydrogen. All right. So now we want to combine those 2 molecules, the tyrosine and the phosphate. So we'll do the same thing we did before. Well, I'm calling it combined 2 this time just to keep them distinct. So once again, we have we're calling on the chem sublibrary of RDKit, and we use this combined mole method. And so I type in tyrosine, put a comma. When I put in the comma, oh, I'm disappointed. I thought it would show me phosphate as an option to put in there. I type the pH, okay, the P, then it shows me phosphate. And so now I show the combined. So we're just following the steps we did before. Now, in this case, we know that the phosphate is attached to the hydroxyl group on the aromatic ring in tyrosine. So it's going to form a bond here. So this oxygen is atom 12. This phosphorus is atom 13. So we're going to make another editable molecule, and I call it editable mole 2 to keep them distinct. And so we have to put 2 arguments in here for this to work. All right, so I'm going to put in, oh, I'm sorry, we've already done that. No, what I'm going to do here is I'm just going to make this editable. All right, so I'm going to put in combined 2 and execute that. All right, and so at this point, I didn't display it. I could have, but I didn't. It would look the same as this. And at this point, we can combine these, and we want to form the bond. So editable mole underscore mole 2 dot add bond. That's a method we can use. And so now I need to indicate the positions that will form the bond. So we're gonna use position 12 here, position 13 here, and then we have the order, which is going to be a single bond. And then we're going to look at it again. And when we do this, we get the phosphate on the oxygen on the aromatic ring. But it's got a hydrogen on that phosphate. That doesn't belong there. So maybe the sanitized mole will pull this off. To be honest, I practiced this. I don't remember seeing that before. So when I do that, it did clean it up. So it removed that extra hydrogen. And so now this phosphorus has the right number of bonds to it. The oxygen has the right number of bonds. So the hydrogen there on the oxygen came off. The hydrogen there on the phosphorus came off. And so those are a few things you can do in RDKit. And if this seemed to go too fast for you, I apologize. I encourage you to go back and use it again. The practice you get from going through it a second time will really help you when you do the crash course on May 1st.